Welcome to Physics 30 Prep Fast Track. We're looking at Lesson 3.1, which deals with circular motion and friction. So, when we talk about the definition of velocity and acceleration, in order for the velocity of an object to change, it must undergo acceleration. Now remember, there are two components to velocity. One is the magnitude of the motion, which is sometimes called the speed, and of course it also has direction. Velocity is a vector, it has direction. Now sometimes the speed can remain the same and the velocity can still change by changing the direction, because velocity is a direction. The velocity of an object can change if the object experiences an unbalanced force. If the unbalanced force is at right angles to the velocity, the speed may not change, but the direction will. This sideways or perpendicular force results in something called centripetal or center-seeking acceleration. All right, a sideways force changes the direction of an object. It may not change the actual speed. So the standard formula for acceleration in a straight line does not work, because the standard definition of acceleration is the change in velocity over time. But if we numerically look at the initial and final speeds, we don't see a change. So what we do is, because speed is constant and it doesn't show an acceleration there, we have to look at the change in terms of circular motion. It's not so much the speed will change, but if the direction changes, then we can combine our basic definition of velocity, which is distance over time, and of course the circumference. As an object goes in circular form, the circumference of a circle is 2 pi r. So if we basically say that the velocity of an object is the time it takes to go in one complete circumference, we can then derive the formula that the acceleration must be equal to either 4 pi squared r squared over t squared or v squared over r. So this is our standard equation for centripetal acceleration. So the velocity will remain the same, but as the object goes in that circular path, it is accelerating towards the center of the circle. All right, so the following equations are used when an object undergoes centripetal acceleration, either v squared over r or sometimes 4 pi squared r squared over t squared. And so centripetal acceleration is caused by the centripetal force acting on the object. Newton's second law helps derive these equations. So if we look at all the equations that we're going to use for both centripetal acceleration and centripetal force, here we go. So we defined centripetal acceleration as v squared over r, and of course since net force is equal to ma, then the centripetal force is just going to be equal to the centripetal acceleration times mass. So if we take this first one, v squared over r, and multiply it by m, we end up with mv squared over r, and this is a standard form. If we multiply our other equation for acceleration, 4 pi squared r over t squared, we end up with m times 4 pi squared r over t squared, and of course we end up with 4 pi squared rm over t squared. And again, not to worry about memorizing these, but understand what each of the terms mean. R is the radius of the circular path. M is the object undergoing that circular motion, and of course t is something we call the period of rotation. That is the time it takes to go through one revolution. And so centripetal force for an object undergoing uniform circular motion, these are the two formulas. So generally on a formula sheet you'll end up with both of the centripetal force or centripetal acceleration equations and both of the centripetal force equations. All right, so the centripetal force is the vector sum of all forces acting to change the direction of a moving object. And it's a result of sometimes tension. If you have a yo-yo that you're spinning around, there's tension in that rope. Sometimes it's due to friction. For when you want to turn your car, then you turn your wheels and the wheels push against the road pushes back, and that friction turns your car into a circle. Gravity, of course, centripetal motion is caused by gravity. The Earth rotates or revolves around the sun. The moon revolves around the Earth. We have lots of satellites out there sending us all kinds of images. Those satellites are in orbit because the gravitational force of attraction keeps them going in a circular orbit. And of course, sometimes, like in our TVs or whatever, there's lots of electric and magnetic forces acting on things like electrons to make them shine on the right point in on a tube, and that tube then glows, and we see a picture on our TV or in our iPod or wherever. So usually in physics 20, we look at tension, friction, and gravity. In 30, we'll look at the electric and magnetic forces acting on a charged body or a charged mass. Okay, so in physics 20, we'll look at tension, friction, and gravity holding objects in circular motion. So when you're driving a car, you can use frictional forces to help you turn the car. As the car approaches the turn in the horizontal road, the driver turns the wheel, which causes the tires to push sideways on the road. And because of friction and, of course, Newton's third law, the road pushes back, giving the car a net force directed towards the center of the circle with a radius that the car follows. And, of course, the force of friction is often equal to the net force. All right? It is also often equal to the centripetal force. So net force and centripetal force are usually equal. Now, if you were on black ice, what would happen is when you turned the wheels, the tires would want to exert a force on the road, but the friction between your tires and the road is based on the nature of those two substances. And if you have black ice, the tires sometimes can't grab onto it. And so what happens is this force doesn't exist. There is no force of the tires pushing on the black ice, and therefore, since the tires don't push on the black ice doesn't push back, and what happens is there's no centripetal force, and so what happens is your car keeps going straight and you end up in the ditch because of the ice conditions. So sometimes what we can do is bank curves. All right, a banked curve will allow gravity to help us to turn through a tight corner, just like in the Olympics, the bikes that race in the velodrome, they have very high banked curves in order to keep their bikes on the track. All right, so it's the same basic principle. They bank the curves so that you don't need as much friction to keep those bikes on the road or on the track. On an unbanked curve, the frictional force depends on the interaction between road and tires. There is something called the coefficient of friction, which is a ratio that describes the stickiness of the two surfaces. If there's black ice, there's not much stickiness, and so the coefficient is close to zero. If it's really, really sticky, all right, and you could think of sliding on a cinder track, that would be very high friction, and of course might be something close to 1.0. All right, that's very high friction. And so we don't worry too much about the coefficient of friction in Physics 30, but you may run into questions that describe it. So the force of friction that acts between two bodies, such as a car going through a corner on the road, the force of friction is going to cause the centripetal force. The centripetal force, of course, is mv squared over r, or the other example we used was 4 pi squared rm over t squared. Now, this frictional force is equal to something called mu, which is the coefficient, as we mentioned over here, times the normal force. Now, on a horizontal surface, the gravitational force pushes down, the normal force pushes up, and of course the gravitational force pushing down is mass times gravity, or the weight, And so the frictional force will be equal to the coefficient times the weight of the object, or the force of gravity acting on the object. So you can figure out what friction is, and then once you know what friction is, then you know what the centripetal force is, and maybe you can figure out what the radius of the curve is, or what's the maximum speed you can go through that curve. So an example is a truck enters an unbanked curve. That means it's horizontal, so that means the only thing keeping that truck moving through a corner is going to be friction. No banking is going on here. So it enters an unbanked curve with a radius of 65. The truck is traveling at 15. What's the minimum force required to allow the truck not to skid off the road? So here's the truck as it goes through that corner. And of course we know that the minimum force of friction is going to be equal to the minimum centripetal force. Since the truck has a mass of 2,800 kilograms and is moving at a rate of 15 meters per second, and the radius of the curve that it moves through, all right, so the radius of this curve is going to be 65 meters, we get a centripetal force of 9692 newtons. The centripetal force is going to be equal to the frictional force required, all right, because it's the friction that causes the centripetal force. So this is the required force of friction, and the coefficient of friction, whatever it might be, has to be high enough for that. So let's say we had a fairly slippery surface and the coefficient of friction was only 0.19. Would that give you enough friction to hold you on the road? Since we need 9692 newtons to hold us on the road, if we only had a coefficient of friction of 0.19, then our force of friction would only be 0.19, that's mu, times the weight of the object. And when you multiply 0.19 times the weight of the object, we only get 5218 newtons of frictional force, and that's insufficient. We need 9692. So with a low coefficient of friction, and this would be on a day where it just rained and the roads are slick, or maybe on a slippery winter morning, the coefficient of friction can be quite low. And if you're going too fast through a corner, if the coefficient of friction is insufficient, or you've got bald tires, then that could be a real serious problem. Now, if we had good dry conditions and you had fresh tires on your car, then the coefficient of friction could be as high as 0.75, and the force of friction in this case would be over 20,000 newtons, sorry, 20,600 newtons, which is sufficient to keep you on the road, and you could move through that corner easily at 15 meters per second. So the higher the coefficient of friction, the more friction there is, and the better it is. So that's why, good tires are better than bald tires. So circular motion caused by friction uses the following relationships. This is the speed of an object as it goes through a circle. These are our two equations for centripetal acceleration. Net force, of course, is centripetal force, and net force is always ma. And then we have our equations for centripetal force. And finally, we can say that the centripetal force on a horizontal road, the centripetal force is caused by the force of friction. The force of friction is mu Fn. If we're horizontal, then the normal force of the road pushing up is the same as the gravitational force of the object pushing down. And gravitational force is mg. So we have a number of equations. Most of these will be on a data sheet. And since friction is often causing and therefore equal to centripetal force, we can say that the centripetal force is equal to mv squared, is equal to 4 pi squared, is equal to the force of friction, and so on, all right? Is equal to mu Fn, is equal to mu mg. And sometimes you can take these two ideas, that is, centripetal force might be equal to mu mg. Or, on the other hand, centripetal force might be equal to mu mg. And once you have these two relationships set up, you can manipulate these relationships and solve for lots of other different variables. All right? So since the centripetal is equal to frictional, centripetal is equal to frictional. Since they're equal to each other, then of course these equations are equal to each other. And different problems will give you different variations using each of these variables. All right? And so that's the premise of the idea of centripetal force is being caused by friction. So let's look at another example. It says a truck enters an unbanked curve with a radius of 82 meters. If the coefficient of friction is 0.45, how fast can the truck travel through the curve and not skid off the road? So remember what we said in the previous slide, that the force of friction is caused or is causing the centripetal force. So the centripetal force is caused by friction. And so, since centripetal force is mv squared over r, and frictional force is mu mg, we can put them together. And manipulating the formula by getting rid of everything except for v squared, that means you divide by m, and you multiply by r. Now one thing we'll notice is that the m on the top cancels the m on the bottom. That's interesting. What it means is, it doesn't matter how heavy the truck is. We don't even need to know the mass of the truck, because our v squared ends up breaking down into mu times gr. So that's v squared, so v is equal to the square root of that. When we do our substitution, we get the speed, the maximum speed of the truck as it goes through that curve is 0.45, the coefficient, and of course times the acceleration of gravity and times the radius of the curve gives us 362, but of course we have to take the square root of that, and that gives us 19 meters per second. Now 19 meters per second is about 68 kilometers per hour. I found that out by taking my 19 and multiplying by 3.6. So again, notice that once the relationship is understood, once we understand that centripetal force is being caused by friction, and we know the formulas for both centripetal and frictional force, then we can put them together and solve for just about any unknown. In this case, we solved for maximum speed. We could have solved for what's the smallest radius that the car can go through without skidding. Because you know, probably from experiences, as you go through a tighter curve, you're more likely to spin out. Let's say if you're at the go-kart tracks, or if you're just riding your bike or whatever. So, as I said, once you understand the relationship and how the formulas work, then you can manipulate these formulas and solve for your unknown. All right?